Hi everyone, welcome to Learning Space. This week we are proud to host team scientists from the Dawn mission that has visited Vesta and is now on its way to Ceres. Before we get started, I'd like to tell you a little bit about what we are and what this is. Learning Space is our weekly hangout where we discuss and by we, I usually mean Nicole Gallucci, who's currently running production in the background, and Georgia Bracey, host a variety of people to come in and talk to you about ways that you can learn and help other people learn about planetary science, astronomy, and space science. With me today, I have Paul Schneck, who's having some technical difficulties, so I apologize if he appears to come in and out of the hangout. We also have, and I should have asked you how to pronounce your last name before I started. I'm so sorry. I have Brett Denevi with us. We also have our representative from the Dawn Education Public Outreach team, Whitney Cope. Now, one of the reasons that this science is so near and dear to us is at CosmoQuest we have the Asteroid Mapper Citizen Science Project that allows you to go in and help scientists, not these two in particular, but help other Dawn mission scientists to map out the distribution of larger craters on Vesta, find the boulders, find features that allow us to better understand the geophysics of this little tiny rock that isn't a planet, isn't a moon, it's its own unique thing hanging out kind of midway out from the sun. The types of things that they're going to be talking about today are, okay, someone needs to mute, there's suddenly an echo. So the types of things that we're going to be talking about today are things that you may eventually be able to see in asteroid mappers as we start adding more and more high-resolution images. We also are going to, at the end of the show, introduce you to a whole bunch of different asteroid educational tools that you can utilize, so stay tuned for all of that. But for now, I'd like to head straight for the science. But first, one last reminder, you can ask us questions by either tweeting to #LearningsPace, leaving us a comment on the YouTube page, or leaving us a comment on the event page that's hosted by CosmoQuest or by the Dawn mission. The best way to make sure that your question gets to us is to leave the comment on YouTube. So Brett, I'd like to start by asking, what is your background and what's the research that you are most excited about sharing about Vesta?
My background is in geology, so I have my undergrad degree in geology and my PhD in geology and geophysics. And it's all frozen now, but hopefully you can still see me.
You look just fine here.
Okay. So, yeah, I also studied spectroscopy in grad school, so I look at using reflectance spectra to understand the composition of the surface.
So to break that down a little bit, what you're doing is different minerals reflect different colors of light in different ways. So by looking at what colors of light are absorbed and reflected by the surface, you can start to understand the composition of different rocks, if I understand this correctly?
Yeah, that's exactly it. And then, you know, Dawn has two instruments that are relevant to that. The framing camera has different color filters that let you get, you know, a good high-resolution picture of the surface in a few different wavelengths. And then there's the spectrometer, which is lower resolution, but lots of different wavelengths, and is really good for picking out what minerals are there on the surface.
And I have to admit, I'm an astronomer. My universe consists of hydrogen, helium, and everything else is called a metal and given the letter Z. So when you start focusing down on individual minerals, what are the different things that you're hoping to find? What are the things that excite you? What is it that is special about different rocks?
Well, for Vesta, part of what's so exciting is that, you know, you have samples with the HED meteorites of Vesta, and then you can have reflectance spectra of those and then tie those back to, you know, the remotely obtained spectra of Vesta. So you can try to get some kind of geologic context for a lot of these samples by picking out, you know, here's a really olivine-rich area, here's an olivine-rich rock. You can start to kind of tie the two together. And it's kind of the reverse of how normal planetary exploration usually goes. You have the remote data, and then if you're really lucky, maybe you'll get samples at some point.
So I have to fess up. My very first time that I attended the Lunar and Planetary Sciences Conference, they were giving all of these fabulous talks where everyone was talking about olivine, and other than the fact that it made a cool green jewelry, I had no clue why this rock was important. So can you bring other non-rock fluent people up to speed on why olivine is so much more than just a pretty gemstone?
Yeah, well, I mean, for one thing, I mean, with olivine and with pyroxene, the minerals that you can really see on Vesta, those are formed in volcanic rocks and basalts, and they also occur in different amounts, whether you're, a volcanic rock that erupts.
Oh, we lost her. Okay. So I apologize. I think that the hangout may have simply gotten verklempt with Paul dropping in and out so much. Whitney, could you possibly call Paul on the telephone and tell him if he's going to keep dropping in and out to maybe not come back in? We're very sorry, and hopefully we'll be able to get Brett back. While I, who am not a Vesta scientist, ad lib, what I'm going to do is introduce all of you to the Asteroid Mappers project. So pardon me while I click over to Quest, and I will share my screen with you. So we're trying to get all of you engaged in not just learning science, but doing science. And you can see everything that I've been browsing recently and tell that I was watching bad sci-fi earlier. So with CosmoQuest, when you go to our website, you can see that we have these 3 different science sites set up along the side, and you just click Let's Explore, and it takes you straight in to, you can read some quick facts, there's some tutorials, and if you just want to get started doing science, click the Get Started button, and it's going to bring up these amazingly interesting and distorted images, because as near as I can tell, Vesta is the rock that was designed by Dr. Seuss. So what we're asking people to do is to just come in and find the craters, click in their center, and drag out to map where the edges of the crater rims are. And this is slowly but surely getting turned into a map. Now what's kind of awesome is beyond just being able to mark craters, there's also boulders, and I think this is no, the shadows are in the wrong direction to be a boulder. I'm not seeing a boulder on this particular image, but there's boulders you can mark. I'm going to do a bad job so that you can just see more images. My data, all of my data gets thrown out fairly immediately. But as you click around on Vesta, what you find is distorted craters that lie on the sides of ridges. So Vesta really is, think that potato that's trying really hard to be a sphere. That's kind of Vesta. Let me see if I can pull up a full-sized image. Actually, Nicole, can you drop me a link for a full globe image of Vesta now that we've lost both our scientists? Whitney, do you want to come in and talk about your new curriculum? You need to unmute yourself.
Yes, I just did. Yeah, absolutely. Let me actually send that along to Nicole, that link quickly here. We adore Asteroid Mappers. We've had all kinds of wonderful opportunities to share out the project in everything from STEM Tech conferences to classrooms, and actually have had a lot of fun by just posting an image just like this one up there, and having participants come up and talk about what craters they see, what they see about the craters, and kind of do a kind of tutorial to engage, and just feel like they can go on it independently. So with that, we have developed some curriculum pieces that could support that a little bit more, something called Visualizing Vesta and Vesta Mosaic, which helps you kind of tune what I think of as tuning your eyes to be able to kind of differentiate different elements of Vesta's surface. So let me send this along to Nicole here. I'm putting in the chat window there, Nicole. There's the website, and let's see here. So I see that Paul's back on. I'm not sure. He's pretty pixelated, huh?
I think he's frozen.
Okay, so we have all kinds of wonderful materials. I think one of the things that's been a great pleasure to be part of the Education and Public Outreach group for Vesta, really working to translate for the Dawn mission, translate the science of investigating both Dawn and both Ceres and Vesta, is that it's a long mission. It's taken us a long time to get out to the main asteroid belt, and with that, we were able to develop curriculum over time that helped, both informal and formal education settings kind of access this cool science. And so we have, as you can see, we have some modules that have some great literacy components. Ion propulsion, of course, is always, very fascinating to all kinds of people. And then we have sets of activities that are sort of, now that we've gotten to our wonderful destinations, what are our next steps going to be? And so the latest two pieces that we have on there are the top two. So here you can see sort of the diversity of what we've got. Vesta Mosaic, in which you take one of these high-resolution images of Vesta, and each participant gets a square of that and gets to kind of look at their square and create their own image using pencils or chalk. And then from there, if you can scroll down a little bit, you can see it a bit better. From there, they're able to, you see, so they sort of look at what an image is. This is the original image of Vesta from Hubble Space Telescope, and the pixels there. Here, Nicole.
Yeah,
and there's
hi.
Paul is here, which is fantastic.
Everyone's back.
Yeah.
Almost.
Yay,
We haven't Brett yet.
almost. Brett, we'll get Brett in a minute. Yeah. And you look terrific, Paul, I have to say, as well.
You don't look like pixelated Hubble Vesta.
No, that's exactly right. Exactly right. You look like, and there's Brett. Yay!
So
at any rate, I'll wrap this up. These are just some fun activities that are great ways to segue into asteroid mappers, backing up the great tutorial that CosmoQuest developed to help lead us asteroid mappers. I'm one of them, to be able to analyze these very cool images from the Dawn mission at Vesta. And I'm going to hush now.
Oh, this is great. I see. Hi, everyone. It's Nicole. Hi. I want to do potato light curves all the way at the bottom.
It is. I'll tell you, potato light curves is the best, and we've actually done banana light curves and sweet potato. We're looking at a lot of diverse shapes, and you really get a very neat light curve, and it's a wonderful way. Something like albedo is so abstract, but with potato light curves, it suddenly is a kick in the pants. And we've had, whether it's whoever you are, whether you're a learner who's 15 or 10 or 55, we've had some people have some great times with that.
So we're going to have to do an entire learning space dedicated to light curves of anything we can, and discussing light curves of actual asteroids, because you can do amazing work. Amateurs are doing amazing work today with backyard telescopes, just measuring how over time and looking at various sites on the planet Earth, we see asteroids occulting stars and varying in their own brightness of reflected light, which brings us back to what Brett was discussing with reflected light. We're so glad that you came back.
Sorry, I don't know what happened.
It's all right. Connections fail, but you were telling us the mysteries of olivine and how it's formed in basalts.
Yeah, well, it's funny because that's actually not even what I work on for Vesta at all. So I mean, yeah, there's a lot of people on the team who are working on that, and I do that for like the moon, and we try for Mercury. But for Vesta, my work all focuses on other things.
Okay, so tell us about what's your work on the Dawn mission and studying Vesta.
Yeah, so well, Paul and I are both participating scientists on Dawn, and so how that works is you write a proposal to NASA, and you're selected to join the team and help carry out your selected research. And so what I proposed to do was to look at how the regolith on Vesta varies, and how it formed and what its depth is. And so the regolith is really just the broken up soil and dust and everything that covers the whole surface of the asteroid pretty much. And one of the reasons I was interested in it coming from the reflectance spectra and that point of view is because you're not looking at just a single rock. You're looking at soil that's been mixed in and churned up and broken up and thrown across the asteroid from great distances. So if you want to look and see how that material, or where the material originally came from, and then how it's been mixed up on the surface as well. Yeah, and so the image that you're seeing is one of the few places on Vesta where you might actually be looking at real bedrock. This is in part of the wall of the Rhea Silvia Basin. And, it's still probably been fractured and, moved to some degree, but you can see, hopefully, in the face of the cliff there's, a big area of rock that's kind of sticking out, and it looks like a little more coherent, whereas around the sides of it you have landslides and superficial, the superficial soil that's, moving around it. And so this is one of the places where you see some of the spectral evidence for the rock types that are thought to have formed, deeper inside of Vesta. And that's exactly what you would expect in this area where you're looking in a huge impact crater in the wall of it that's exposing some of the interior of Vesta. And so, we kind of look for places like this and other smaller areas where you can find some rock that might have actually, formed in it originally right in that spot instead of being mixed up and with all the other rocks.
And one of the really awesome things about Vesta is because it has been hit hard by so many other objects. There are places where impacts have essentially dug trenches for us to see what are the other soils, what are the other mineralogies at different depths within. That's kind of cool. So Paul, can you tell us, and hopefully your connection will stay, can you tell us about the type of research that you're doing as a participating scientist? You're muted.
Yeah, I'm muted. Yeah, I basically had to reboot and then launch a different browser, and it seems to be stable now. So you try every trick in the book, and hopefully it'll last. But yeah, I'm in the same situation that Brett is in, and I started out not being terribly interested in Vesta, but I became interested in it when I realized that the mission was actually going to go to Ceres after it finished with Vesta. And Ceres is the largest asteroid, but it's interesting because it has a lot of ice. And Vesta comes into it because you have two bodies that are very similar in size, where you've got a lot of impact craters probably formed on them. One has got no ice on it at all, or hardly any ice at all, and one has a lot of ice on it, theoretically speaking. So there's a direct comparison we can make. And you're exactly right. Impact craters dig trenches. They're basically free drill probes. On Earth, we use large drilling apparatuses to drill 10 or 20 kilometers down into the crust of the Earth. And we can't obviously do that. It's very expensive to take a drilling rig out to the solar system. Not to mention the life support that would be required. It's just very heavy machinery. So we use impact craters to dig deep and excavate material up under the surface. And that's one of the things we're looking at on Vesta, is what are the underground materials. is there olivine? I didn't hear the earlier conversation, but I did hear you were talking about olivine, and that's one of the things we were looking for, is to see, is the mantle of Vesta got a lot of olivine on it, like the Earth does? And we're having a lot of trouble finding it, but that could be because the olivine is very hard to detect. But again, I wasn't part of that conversation. But one of the other things that we can look at is the basic morphology of the crater. What is the structure? And that actually is controlled in large part by gravity. Now, I had to write down these figures, but they're interesting to note that the surface gravity on Vesta is only 2.5% that of Earth. That's a very low gravity field, and if you want to take out a weight machine and weigh yourself, that would be an interesting place to do it. But it's also 15% of the moon's gravity, and that's where my work comes in, because what I'm doing is comparing morphologies of impact craters on the moon versus those what we're seeing on Vesta. We're actually able to look and see how does the impact process itself differ depending on what the gravity of the body is that you're looking at.
And this is basically a matter of if something has more gravity, the way the crater is going to evolve over time is going to differ in terms of what sort of slumping happens on the edge. So if you've ever dug a hole on the beach, you may have experienced, if you dig the hole deep enough, bad things happen to the hole. And craters are...
That's exactly right. And it's not only long-term deformation, but it's also controls how the crater forms in the first few minutes. And can you show a slide for me? The Vesta moon crater slide. Can we show that slide? Yes. I like to show this slide because I don't label it, which is Vesta and which is on the moon. There's two craters shown here. They're both about 20 kilometers across, which is, I can never do the calculations, about 10 miles across, something like that. On one side is a crater on the moon, the other side is a crater on Vesta, and I asked my colleagues to guess which is which. And there's actually not a lot of difference between the two. If you look on the sides of the impact crater, you see these narrow little deposits on the flanks. You can also see some of the regular outcrops that Brett talked about on the left-hand side. You also see these long, narrow things coming off the sides, and those are actually small-scale debris slides. It's the kind of deformation that happens when you form a large crater. It's a big, deep hole. The slopes of the crater are 30 to 40 degrees. That's kind of unstable, so it wants to collapse, and gravity forces that. And as it turns out, the one on the left is the Vestan crater, and the one on the right is the lunar crater. And the big difference between the two is that, and these are both the same size, same scale images, the lunar crater has a lot more debris on the bottom. And if you look at the right-hand image there, you see that there's this rolling kind of hill deposit on the bottom of it. That's actually a deposit of impact melt with broken up impact debris. Now, Brett talked about regolith being formed of broken up rocks due to impact. The dog's interested. Okay, that's good. And what happens is that the impact generates a lot of heat and breaks up a lot of rock because it's of high velocity. This asteroid hit at 5 kilometers per second probably. So it's melting a lot of rock, breaking up a lot of rock. And on the moon, the impact velocity is even higher. It's more like 15 kilometers, almost 20, more like 20 kilometers per second. And that high velocity means that the moon creates a lot more melt and a lot more impact debris. And that's what we're seeing in the bottom of the lunar crater. But otherwise, the two craters are pretty darn similar, which is actually quite reassuring that the impact process is working pretty similar on both bodies. So I don't know. Anybody want to talk about anything else, or I can show a few more slides? Do you want to go back to Brett now, or?
Well, I think one of the interesting things that you've introduced here is um, with the impact process, you're dredging down, you're revealing different things, and your interest in getting tied into this was brought in part with Ceres and the fact that we do have these two asteroids, one of which is on the icy side of the asteroid belt and one which is on the baked dry side of the asteroid belt. And if you could explain how this ended up happening and what this means, and maybe bridge into I'll give you a sneak preview, volatiles, which are coming in the future, that would be awesome.
You mean how Vesta ended up with no ice and Ceres ended up with ice? That's a tough question. It gets back to the formation of the solar system itself and the fact that the sun is warm, and as the planets began to accrete from small particles, you can think of the rings of Saturn as kind of almost analogous to that in some ways. Small rocky pieces and icy pieces of different sizes, they begin to slowly accumulate and grow into larger and larger planets. But there's a zone where water ice is not stable and tends to remain a vapor and doesn't accrete very much, and is actually driven off by the solar wind. And I'm kind of mixing a lot of these concepts together, but the general principle, and hopefully Brett can correct me on some of this, is that that transition where water ice becomes a stable mineral and can form clumps and solid particles is somewhere in the middle of the asteroid belt. Jupiter has a lot of icy satellites, whereas Mars and the Earth have rocky satellites. And Venus and Mercury have none, but still, they're dominantly rocky bodies. So even though the ocean is 4 kilometers thick on the Earth, that's not very much when you think of the mass of the Earth. So Vesta and Ceres are on either, just very close on either side of that transition zone line, where ice is unstable and it becomes stable again. Now, we don't really know for sure how much water ice is really in Ceres, but we think there's quite a bit. It may be up 30 to 40%.
And what's been kind of awesome is there's been surprising evidence that so in science we like to use fancy words for things that aren't that fancy. So we use the word volatile for anything that will basically turn to gas if you get it hot enough. So water is a volatile, carbon dioxide gas, dry ice basically, is a volatile. So all of these different things that we use to cool drinks at the bar on Friday night, those are volatiles. I was about to ask Brett a question, and she's still
She's having the same problem I have, where the lights go out automatically.
Oh, yeah. Right. Yeah.
I did. Sorry, they're like on a motion sensor, which is behind something that can't see me. So.
We have that problem at work all the time. You're working really hard and diligently, and the lights turn off on you. So they're finding evidence that even though Vesta's on the bake dry side of that line, that there still were volatiles. So can you explain a little bit about that, Brett?
Yeah, so, like Paul said, Vesta wasn't expected to have a lot of, volatiles that were native to the body. And, what volatiles it did have probably when you had these volcanic eruptions, into a vacuum with no atmosphere, you probably lost a lot of, water and the gases that were erupted along with the magmas. So one of the interesting things that we saw came in a couple forms, actually. It was kind of a neat thing where each instrument on Vesta contributed something to the picture, where we had from the gamma ray neutron detector evidence for hydrogen on the surface. And so they can measure, elemental abundances, and hydrogen was starting, they started to find it. And not, in permanently shadowed craters at the poles, like has been found on Mercury or in the moon, but right, in broad areas across the equator. And when you look at where those occur, they were related to dark areas on the surface of Vesta. And then the spectrometer could also see evidence for hydroxyl in the reflectance spectra in those areas. And then when we looked with the
big word again, hydroxyl?
Sorry, yeah, so you can see absorptions in the reflectance spectra that can either be due to water or to OH. And you can't always tell those apart. So to be conservative, we say just the OH part, the hydroxyl.
Which is a fancy way of saying things like alcohols, which is far more cool to think about.
Yeah, and it's so all of this, you know, hydroxyl or water is completely implausible to be in the form of, you know, like water ice or some kind of thing that's just sitting on the surface, because Vesta gets, you know, plenty warm and there's no atmosphere, so it's not going to be stable near the surface or on the surface. So there's not, you know, big piles of ice or anything, but what you do have is water or these hydroxyls that can be bound within the minerals. And that was actually seen in some of the Vesta meteorites, where it's not coming from the Vesta part, it's from little clasts of exogenic material, things that are land on the surface, come from, you know, other meteorite impacts, get mixed in with the soil. And so what we think when you put all the different evidence together is that you have carbonaceous materials that are, you know, from the results of impacts. And when you have those kinds of impacts, you know, usually on like the moon or Mercury or somewhere like Paul was talking about, those happen at really high speeds. And so you totally vaporize most of the projectile. And those volatiles, like you said, are lost. But on Vesta, the impact speeds can be a lot lower in the asteroid belt. Things aren't hitting quite as hard as Paul mentioned, so you can kind of preserve some of this foreign material that has its own water and keep that on the surface.
So this is really an awesome story that I want to pull apart a little bit.
Yeah.
So basically what's happening is you had happy little Vesta orbiting in the asteroid belt. And it's not Han Solo's asteroid belt. If you're standing on Vesta, you're not really going to see another asteroid. But now and then things do get close to one another. And at different points in our solar system's history, something rich with waters, with alcohols, these hydroxyls, other forms of volatiles, so think comets, have come along, and they've had the types of orbits that allowed them to have a slow motion collision. So it wasn't anything too traumatic. The volatiles survived the impact. But then something more violent happened along the lines, causing chunks of Vesta to get thrown into space, where they started this amazing journey where chunk of Vesta that's carrying part of that comet that came along, that exogenate volatile that got embedded in the rock. So something hits Vesta, throws up rocks. Those rocks end up on wild orbits that eventually end up carrying them all the way back to Earth, where scientists like you guys, hello?
We can see you. We can hear you.
Okay, my video temporarily went away. So this is scientists like you can go down to Antarctica, collect rocks, look at the spectra of the rocks, and realize, hey, this thing reflects light the same way Vesta reflects light. We have a chunk of Vesta. So that's just an amazing set of multiple collisions that took part to get that sample to your laboratory.
Right.
Yeah, absolutely. And then what's kind of neat is that we can see in some of these craters that happened, you know, after, it's not just comets, but, you know, pieces of other asteroids that, you know, like Paul was saying, may have formed farther out, had more water in them, and, you know, got mixed into the regolith on Vesta. Then later impacts came in at, you know, sometimes higher velocities, and basically all that water, the heat from the impact, heated up so high that it's not stable anymore, and it starts to, you know, degas into space. And so I had some of the pictures of some of the pitted terrain is yeah, should show this, but yeah, this is a perfect one. So the crater, the kind of context image on the left is of the crater on the bottom is the crater Marcia, one of the biggest young fresh craters on Vesta. And on the right-hand side, you can see the floor of the crater. And hopefully you can see this kind of unusual texture on the floor.
5 kilometers across, by the way.
Yeah, yeah. Well, it went away, but the scene on the right is, yeah, about 15 kilometers across, I think. Can you guys still see it? I see it as like a teeny little box, but
yeah, you have to click on it to see it big. Pamela does it for the audience.
Oh, okay, sorry. So yeah, there we go. So you can see all these little pits that are on the floor of the crater, and we think that these formed when you had this water basically degassing from the hot material after this impact crater formed. And as the water kind of degassed, it left behind these little, pits that have actually also, we haven't seen anything like them on the moon or other asteroids that we've seen at high resolution, but we have seen some of them on Mars. And we have another picture that hopefully shows that comparison. Yeah, there it is. So you can see hopefully how similar these look to the Mars examples. On the left two images are images of the floors of craters on Mars, and then on the right-hand side is Vesta. And so these kinds of pits have been described as almost like soap bubble kinds of geometry, where you had these volatiles kind of bubbling up in the forming these pits where they started to kind of coalesce and grow, and then once it's done degassing, you're left with these really unusual shapes, which were clearly pretty unexpected for Vesta, where we thought it would be just dry.
Oh, now we're back on air.
Okay.
You're muted, Pamela.
Sorry about that, folks.
We're back on air.
I unscreen saved, and it decided to eat my transmission. Today is the day for chaos. Okay, so we're back. You've now seen pitted terrains. Now, we have pitted terrains we're learning. We have interesting minerals, including the ever-mentioned olivine, which still makes great jewelry, even if you do find it on other planets, and rocks. What other sorts of awesome terrains are the two of you finding? Paul, what's your favorite thing that's been found on Vesta that wasn't anticipated beyond just all the images of it are just so much smoother than what we see for the Moon and Mercury for similar sized features?
Well, a couple things. One is the large impact basin at the South Pole, which has got a very unusual and complicated geology, and we can talk about that at some other point. But one of the other surprises, I guess, was these odd-shaped craters, which I like to call bipolar craters. And if you could bring that slide up, we can talk about those.
Is this the Rootney?
Antonia.
Antonia, okay.
Antonia. And what I mean by bipolar is really the bimodal or asymmetric craters, is that they really seem to have a split personality. And normally in a crater, usually it's pretty symmetric. You've got a rim around a circular rim and a central peak, and you've got terraces and whatever else. It's pretty symmetric, more or less. And this slide here shows a couple things. Let me bring it up. one, it highlights the amazing data sets that we've acquired, and I'll go through them for you so you understand what they are as we go from left to right. The first image is the base mosaic, which is basically the global coverage in the single filter that we have and the clear channel at about 20 meters from about 75% of the surface and 70 meters for the entire surface. And then we also have high-resolution color imaging. I think that was in, I want to say, 7 or 8 filters. Do you remember what that was, Brett? I can't remember exactly what it was. But we also have infrared spectral measurements out to about 5 microns, I believe, as well. So that frame illustrates that we got some good high-resolution color. The third frame is topography, which is at about at least 70 meters resolution or better. So we got high-resolution topography. It's color-coded so that blue is low and red is high in this particular case. So you can see it's sloping off pretty steeply to the bottom of the frame, which is an important clue to what's going on. And from the topography, you can also get the slope, how steep the surface is at each individual point on the surface. We also have the elemental abundances that we talked about earlier as well, but that's a very low resolution. It would have basically 1 pixel in this scene. And this is Antonia crater, about 17 kilometers across, and which is right in the center of the scene, and there's some other craters around it as well. This is actually on the floor of the giant impact basin, so it's pretty large basins, about 500 kilometers across. You hardly see any of it here. And let's see, can we zoom in on the first panel? Is that possible? Yeah. Or the third panel, actually. Yeah, that's good. That's good. You see how asymmetric this is. And what I mean by that is that the bottom half of the crater, I'm sorry, the top half of the crater, which is to the north, on the steep slope, has got a classic shape to it. Basically a steep scarp. It's got these debris slides, small little bitty debris slides coming off the rim, all going down towards the center. It's all very normal and happy. But on the bottom half, it doesn't have that at all. It's got this rubble strewn slope. It's rounded. It looks like it's 2 different craters that formed at the same time, but it's in fact one large crater. And we didn't actually recognize this landform very much until recently. We're starting to see some of it in the lunar orbiter data that's been coming down. There's a handful of lunar craters that look like this, but Vesta has a high proportion of these craters. There's like 100 of them scattered around. It turns out that they're actually formed on, you see them on steep slopes, steep regional slopes. And there's a couple things we think that's going on. One is that when you hit the side of a slope at an angle, I guess I can't show it. It hits like this, and it blasts material up. And because of the fast rotation of Vesta, about 5 hours, and also the steep slope, that material actually falls back down on that side and is not symmetric. The other odd fact is that all of the areas that have the steep scarps, the failed scarps, are on the high standing side. That means that is the part of the crater that has failed. It indicates that part is its strength has been exceeded, and you get the standard slumping that you get, the rim slumps. It's kind of a complicated mess between these 2 different processes, the asymmetric fallback of the ejecta and the fact that you've got one side of the crater is one side's steep like this and the other side's shallow like this. So this part fails, the material comes off the rim, and the other part doesn't. So you get these odd shapes. Let's see if we can scan over to the second panel. You can see the color. I don't know if it's possible to explain that on the web, but I made a stab at it. you also see these odd colors, especially on the south west side. You get this dark material coming off the side that's been ejected out onto the surrounding terrain. You also get some yellowish materials. I'm not sure, Brett. Is this some of that dark carbonaceous material? Do you think this is an example of that?
Yeah, I don't know. It could be, but some of the dark material people have thought is impact melt or buried pyroclastic. So I'm not sure about this example.
Yeah.
And I'd like to cut in that this is not true color. Vesta, if you get close enough, does not become funky fluorescent green. This is a whole variety of different, very narrowband filters that people have faked the color on.
Yes, it goes out just into the near infrared, just beyond.
Except it's not fake color; it's enhanced.
It's Superman vision, I guess. Because he can see out into the infrared and the ultraviolet. So we're basically just pushing the edges of human vision out, not too far in this case. We're not out in the 5 micron band at all. We're about 1 micron, and usually the human vision goes out to about 0.6 or 0.7. So we're at about 1 micron, I think, 0.95, something like that. So it enhances the color differences. The color differences are real, though. And the color's been stretched a little bit to make it look wonky, but it's a nice picture because it shows, and the green stuff, we should make a note, is not olivine, but might have a little bit of more olivine in it than normal. It's actually characteristic of something called diagonite. And diagonite is, correct me, Brett, but I believe it's the mixtures of the other, it's a regolithic mixture of the other meteoritic types, is that right? That we got from Vesta?
Howardite.
Howardite is the mix, is that right?
Yeah.
That's right. And, so diagonite is believed to be the deeper rooted rock type of the 3 Vesta meteorite classes that we have. The other is eucritic. They're all basaltic in general composition, but the diagonite has larger grain sizes, I believe. And this is again on the floor of the Reyes Sylvia Basin, which is 500 kilometers across. It's supposed to excavate the mantle. So
the Reyes Sylvia crater is that awesome crater on the south end of Vesta, where Vesta basically looks like it got its derriere smushed in by an incoming impact.
Which then is that the one that causes the ripples further out?
Yeah.
Yeah.
It's grooviness.
Yes, the source of its grooves.
It had a couple effects. It blasted a couple kilometers worth of ejecta out onto the surface all around the equator, and it appears to have formed large-scale fractures that basically ring the equator of Vesta as well, and also may have created a whole series of small-scale fractures. So it had a pretty dramatic effect, but it also definitely excavated deeper material than we would normally have seen on the surface, and it is actually it is actually the dominant event that produced, or actually sent, those meteorites to us. It's the only, there's 2 impacts that could have done it. But this is the most recent one that could have actually launched all those meteorites off of Vesta into the asteroid belt, where they got circulated around, and some of them came to Earth. Mm-hmm. And there's probably there's thousands of tons of those meteorites still out there in the asteroid belt, and eventually they'll find their way to other planets.
So I want to remind you guys, if you have a question or comment before we start wrapping up, you can use the YouTube channel. I'm watching you guys there. And the event page as well. If you're using Twitter, use the hashtag #LearningSpace. That'll show up in our comment tracker as well. And I've posted a couple links in the event page comments, which I will also include in the YouTube video description when it's all done. I don't know if Pamela's trying to talk, but she's muted.
No,
Okay.
I was waiting to see if someone jumped in. So I'm going to take advantage of this moment to pull up a picture of olivine, because really we keep mentioning it. It's worth seeing what it is. And if the two of you could get one interesting piece of science about Vesta out that justifies why the Dawn mission is on its way out there, what piece of science would you want everybody out there to know? And while you think about answering that, Nicole, could you tell people what are the next Hangouts coming out?
Oh, sure. So the next Hangouts we have coming up today is Wednesday. I do this every week. I go, what day is it? Tomorrow, I don't know if there's a Planetary Society Hangout scheduled, but those are usually on Thursdays at noon Pacific. Friday at noon Pacific, we will have the weekly space hangout. All your favorite space journalists will be going over the news from the week. I don't know what we're going to be talking about yet, because we've got a few stories in the queue, but whatever else happens in the next couple days. And then Sunday night we have the virtual star party with our amateur astronomers from around the globe showing their telescope views. While we look at a pretty picture of olivine. And Monday is Astronomy Cast, episode 301. You guys hit the 300 mark last week, so yay!
It was kind of awesome. I can't believe how long we've been doing this. But this is olivine. This is the thing that I think planetary scientists talk about more than any other specific mineral, which as an astronomer I find highly amusing. I don't know why. I can't explain it.
Is it because it has nothing to do with water? Is that...
Well, it's the most abundant mineral on Earth, so
Okay.
By
it's
far
a rock.
the most abundant mineral on Earth. Except we can't get to it very easily. It's 50 kilometers down. So.
So that means that if we uncovered 50 meters, you said?
Kilometers.
50 kilometers. That's a bit harder.
A little bit further.
If we removed the top 50 kilometers of the Earth would look like this pretty rock.
Oh, a giant gemstone, I guess, if you want to put it that way.
These are just interesting things to think about. I know lots of science fiction writers, some of whom are watching this, waving at PG, who we know is out there.
Yeah, but just because you mentioned it, I mean, the olivine is so interesting, because you have places that are huge craters that, on the moon, or for example, ripped off 50 kilometers of the crust, and you can see some of this olivine in the mantle. So you want to know what the inside of the moon or Vesta or any planet is made out of, and this is kind of giving, when you see that abundant olivine, you're kind of getting a look into the mantle.
So this has been a great whirlwind conversation about many different varied things with Vesta. If you out there in the audience would like to do your own Vesta investigations, check out Asteroid Mappers. Go to cosmoquest.org, click on the Vesta Mappers link on the landing page or under Do Science from anywhere on the website. We are getting ready this evening to send out a newsletter to everyone who's involved. We're going to do a one-time spam of the entire community to make sure that people know that this exists. If you don't have an account on CosmoQuest, you won't get our newsletter. So go set up an account if you haven't yet. We'd like to remind everyone that if you want to learn more beyond just exploring Vesta using asteroid mappers, there is a whole series of educational materials that the Dawn folks have put together that are on their website and are also available through NASA Wavelength. And we're getting ready to develop our own educational materials highlighting asteroid mappers. So if you'd like to investigate Vesta, I think we're actually saying investigate.
Yes, I think we have submitted an abstract for next year's National Science Teachers Association conference with that title, so we're locked in.
Okay, so we're going to be developing materials, and if you are a school teacher or an outreach person or just like to communicate science to others and you have ideas, let us know. We will always give you credit, and we're happy to run with great ideas. So it's been great. Go ahead. Yes, Whitney.
I mean, it's we want to partner with you, and we love anybody's great ideas too.
Yes.
For things that you think would help, just illustrate, help us translate this fantastic science that Brett and Paul have been sharing. We're behind you too. So collaboration is brilliant.
That's awesome. So I'd like to give our parting words to our two scientists. So what things would the two of you like everyone to know? Paul, I'll go ahead and start with you.
I would say that the thing that comes out of this, to me, is Vesta as a whole body. And this is the first time we've actually looked at a large planetary body in the asteroid belt between Mars and Jupiter, in that transition zone between the dry, rocky part and where you begin to get stable water ice. And Ceres is an important component of that. I mean, we've looked at smaller asteroids before. The largest one, I think, has been about 50 kilometers across, I think. And they've been chunks, basically things broken off from other objects or things that never really got very far. But this is the first time we've really looked at what we call a protoplanet, a planet that basically just barely began to get formed. And we were really surprised by the geologic complexity, these troughs, these large impact craters, the deposition all across the equator, the amazing color differences that we've seen. Orange craters, and red craters, and green craters, and values here. But it really surprised us, I think, and pleased us. We were very, very pleased that we had something interesting to study, not just a boring old rock. With a lot of geologic complexity, we're actually seeing for the first time what went on in this transition zone in the asteroid belt. And Ceres, in a little less than 2 years, is going to be the next key to unraveling that. I mean, the solar system is just a big, giant jigsaw puzzle, and this is an important piece in that.
Yes, well, so for me, I guess what I really like about not just this mission, but all the other missions to asteroids and everything, is that each one is really gives you a feel for how unique and how much diversity there is in the solar system. We visited a few asteroids with spacecraft: Eros, Itokawa, Vesta, and each one has had really surprising, distinct features. Ponds on Eros, this weird pitted terrain. Each one is its kind of own interesting geologic body, and so it's really exciting to think about what will the OSIRIS-REx target asteroid, I forget, it just got named, I forget what it's called now, but what will we find there, and all the exploration that leads to these really distinct worlds that you can go from Vesta being a tiny pinprick of light in the sky to kind of a fuzzy blob from Hubble, to this very detailed picture where we're starting to look at such interesting and complex geologic processes and evolution that can tell us about what happened and what's going on in the early solar system. And that's one of those things that, even though you're just kind of focusing on your little science question every day, it's the the awe and the wonder that made you get into this field in the first place.
Cool. Well, thank you so much, you guys, Brett and Paul and Whitney, and Pamela's currently muted because there are dogs barking in the background. So, thank you, everyone, again for joining us and sharing the Vesta science with us and helping us do the science on CosmoQuest. And we'll see you next week.
Great.
Hi everyone, welcome to Learning Space. This week we are proud to host team scientists from the Dawn mission that has visited Vesta and is now on its way to Ceres. Before we get started, I'd like to tell you a little bit about what we are and what this is. Learning Space is our weekly hangout where we discuss, and by we, I usually mean Nicole Gallucci, who's currently running production in the background, and Georgia Bracey, host a variety of people to come in and talk to you about ways that you can learn and help other people learn about planetary science, astronomy, and space science. With me today I have Paul Schneck, who's having some technical difficulties, so I apologize if he appears to come in and out of the Hangout. We also have, and I should have asked you how to pronounce your last name before I started. I'm so sorry. I have Brett Denevi with us. We also have our representative from the Dawn Education Public Outreach team, Whitney Cope. Now, one of the reasons that this science is so near and dear to us is at CosmoQuest we have the Asteroid Mappers Citizen Science Project that allows you to go in and help scientists, not these two in particular, but help other Dawn mission scientists to map out the distribution of larger craters on Vesta, find the
meteorites of Vesta, and then you can have reflectance spectra of those and then tie those back to, the remotely obtained spectra of Vesta. So you can try to get some kind of geologic context for a lot of these samples by picking out, here's a really olivine-rich area, here's an olivine-rich rock. You can start to kind of tie the two together. And it's kind of the reverse of how normal planetary exploration usually goes. You have the remote data, and then if you're really lucky, maybe you'll get samples at some point.
So I have to fess up. My very first time that I attended the Lunar and Planetary Sciences Conference, they were giving all of these fabulous talks where everyone was talking about olivine, and other than the fact that it made a cool green jewelry, I had no clue why this rock was important. So can you bring other non-rock fluent people up to speed on why olivine is so much more than just a pretty gemstone?
Yeah, well, I mean, for one thing, with olivine and with pyroxene, the minerals that you can really see on Vesta, those are formed in, volcanic rocks and basalts, and they also occur in different amounts, whether you're, a volcanic rock that erupts.
Oh, we lost her. Okay. Boulders, find features that allow us to better understand the geophysics of this little tiny rock that isn't a planet, isn't a moon, it's its own unique thing hanging out kind of midway out from the sun. The types of things that they're going to be talking about today are, okay, someone needs to mute, there's suddenly an echo. So the types of things that we're going to be talking about today are things that you may eventually be able to see in asteroid mappers as we start adding more and more high-resolution images. We also are going to, at the end of the show, introduce you to a whole bunch of different asteroid educational tools that you can utilize, so stay tuned for all of that. But for now, I'd like to head straight for the science. But first, one last reminder, you can ask us questions by either tweeting to #LearningsPace, leaving us a comment on the YouTube page, or leaving us a comment on the event page that's hosted by CosmoQuest or by the Dawn mission. The best way to make sure that your question gets to us is to leave the comment on YouTube. So Brett, I'd like to start by asking, what is your background, and what's the research that you are most excited about sharing about Vesta?
My background is in geology, so I have my undergrad degree in geology and my PhD in geology and geophysics. And it's all frozen now, but hopefully you can still see me.
You look just fine here.
Okay. So, yeah, I also studied spectroscopy in grad school, so I look at using reflectance spectra to understand the composition of the surface.
So to break that down a little bit, what you're doing is different minerals reflect different colors of light in different ways. So by looking at what colors of light are absorbed and reflected by the surface, you can start to understand the composition of different rocks, if I understand this correctly?
Yeah, that's exactly it. And then, Dawn has two instruments that are relevant to that. The framing camera has different color filters that let you get, a good high-resolution picture of the surface in a few different wavelengths. And then there's the spectrometer, which is lower resolution, but lots of different wavelengths, and is really good for picking out what minerals are there on the surface.
And I have to admit, I'm an astronomer. My universe consists of hydrogen, helium, and everything else is called a metal and given the letter Z. So when you start focusing down on individual minerals, what are the different things that you're hoping to find? What are the things that excite you? What is it that is special about different rocks?
Well, for Vesta, part of what's so exciting is that, you know, you have samples with the HED.
So I apologize. I think that the Hangout may have simply gotten verklempt with Paul dropping in and out so much. Whitney, could you possibly call Paul on the telephone and tell him if he's going to keep dropping in and out to maybe not come back in? We're very sorry, and hopefully we'll be able to get Brett back. While I, who am not a Vesta scientist, ad lib, what I'm going to do is introduce all of you to the Asteroid Mappers project. So pardon me while I click over to Quest and I will share my screen with you. So we're trying to get all of you engaged in not just learning science, but doing science. And you can see everything that I've been browsing recently and tell that I was watching bad sci-fi earlier. So with CosmoQuest, when you go to our website, you can see that we have these 3 different science sites set up along the side, and you just click Let's Explore, and it takes you straight in to, you can read some quick facts, there's some tutorials, and if you just want to get started doing science, click the Get Started button, and it's going to bring up these amazingly interesting and distorted images